It's my pleasure today to introduce Professor Noel Clemens from the University of Texas at Austin. So Noel did his undergraduate degree at the University of Massachusetts, then a master's and PhD from Stanford University. Then he was a postdoctoral fellow at Sandia National Lab. And then he started his academic position at UT as an assistant professor all the way to professor. He was also the department chair at UT for the Aerospace Engineering Department from 2012 to 2019. And he's won several awards over his time there, including most recently the AAA Aerodynamic Measurement Technology Award in 2022. He's a fellow of AAA and APS, and he's also served as the editor-in-chief of Experiments in Fluids for a few years. And he's worked for a pretty long time on unsteadiness of, in supersonic flows and hypersonic flows. And today he's going to talk to us about unsteadiness of shockwave boundary layer interactions. So over to you, Noel.
Yeah, well, thank you, Barth, for the nice introduction. So it's really a pleasure to be able to speak to you today on this topic that we've been working on for many years, like probably over 20 years. And let me just acknowledge first some people that I've collaborated with, and I'm going to give a bit of a historical kind of overview of our role in this topic over those years. And so David Dalling was a colleague and mentor of mine. Bharath here was a postdoc in our lab, and we had some great students like Steve Barish, Justin Wagner, and Eugene On, and then postdocs Leon Vanstone, Mustafa Musta, and Mark Eitner, who've contributed to the work I'm going to show you. And then this work has been sponsored over the years by the Air Force Office of Scientific Research and the National Science Foundation in the US. Okay, so let me just give you a bit of a motivation for this topic. It's like, why do we care about these shock boundary layer interactions? First of all, they're just a common feature of high-speed flight. And essentially, anytime, if you have a vehicle that's flying, anytime you have the body of the vehicle sort of juts out in almost any way, you're going to have at least a compression or more likely a shock that forms. And so, for example, on the underside, the compression surface, as it's leading into the inlet, you have these shocks that are formed. And if there's a boundary layer, obviously that there'll be a shock boundary layer interaction. On the sides here, you have what looks like a blunt fin interaction. On the control surfaces, such as the flaps or ailerons, you're going to have what looks like compression ramp interactions. Of course, all these interactions are 3D and fairly complex. And so, but the problem with them is that the separation will lead to loss of control authority. And then also a bigger problem in hypersonics is that the flow gets, obviously due to the viscous heating, that you have high fluctuating heat transfer rates that are, well, first of all, high mean heat transfer rates, and then the unsteadiness induces additional heat transfer due to that, due to the increase in the gradients. And then the unsteadiness can couple into the resonant frequencies of aero panels, and especially in hypersonics, the panels get weaker because they get hot, and they become more compliant, and so then they exhibit a much bigger vibratory response to the forcing of these unsteady motions, and then they can lead to structural fatigue and failure. And there's just an example of that this is the X-15, and it's actually the Schlieren image that's behind me in my background. But this thing is something that flew in the 60s, and it basically was a rocket-powered airplane. It flew up to Mach 7, and is really kind of an incredible vehicle. But they used it as a test bed for engineering development, and so one experiment they did is they had a ramjet that they hung off of a pylon on the bottom of they put on the bottom of the vehicle, and this shows that this is the pylon and this is the ramjet. Then they had some pitot probes and thermocouples that were they instrumented because this was a research project. And then off of that cone of the inlet, there's actually a double cone. So you have a shock wave that's formed, and then another shock. And then because there's a shock boundary layer interaction, that this whole shock system is highly unsteady. And so it is sitting there vibrating back and forth. And at this triple point, there's what's called a supersonic jet. It's sort of this high momentum a jet that shoots out, and it's basically impinging on the pylon. Now there's the shock boundary layer interaction, or SBLI, is highly unsteady, and it did this to it in flight, which is you can see that this panel has the pylon had completely fatigued and failed, and then the ramjet is here on the ground. That they found that it just fell off, right? And so these things are important. They have very big implications in terms of the design of the aircraft, because you have to design around the problems associated with these the fluctuating loads. Okay, so just another example. This is the UHF antenna on the X-15, and just showing you after the flow that it looks very much like what's called a blunt fin interaction, and you can see this horseshoe vortex where things are all burned up, and again, a lot of that's mean heating, but it's also unsteadiness contributes to a damage to the vehicle. Okay, so I'm going to talk about a compression ramp interactions, and they're a little different from some other interactions in some of their features, but so this basically, you have a supersonic flow. Let's say flow goes from left to right, and you have a compression ramp, and then in your inviscid theory or compressible flow courses that you can take, that there will be an oblique shock that is generated off of that ramp. And in an actual viscous flow, that it tends not to be. What happens is that due to the adverse pressure gradient across the shock, the boundary layer will separate, and it will cause the shock to exhibit what's called upstream influence. And so it exists well in front of or upstream of the obstruction that's causing the shock. And so this is the separation shock, because the flow separates and the streamlines deflect upwards. And so that is what causes the separation shock. And then where it touches the wall, that's called the separation shock foot. Technically, it never touches the wall, because in order to have a shock, you need supersonic flow. But at some point, the velocity goes to zero, or Mach number goes to zero. And so it only exists up to the sonic line. And that's about, like in our wind tunnel, that's about 100 microns from the wall. You go far out, then it reaches that inviscid shock angle that you'd expect for whatever wedge angle this is. Well, this whole system is unsteady. The shock's unsteady, the separated flow's unsteady. They're sitting there oscillating. And this sort of the range of separation, or just call this the length scale. There's a separation length scale, and then this Li, and this is actually not the scale. The Li is bigger, about half as big as the separation length scale. But the Li is what's called the intermittent region. It's the region over which this shock foot is oscillating. So this is just an example of a surface flow viz, where we have oil doped with a fluorescent dye. And this is a compression ramp here when we're looking down on the flow. And so then this shows a wind tunnel startup, and then the establishment of the interaction. And so where you see these streamlines are sort of, the flow is moving upstream, and then it's meeting the flow going downstream. And this is what's termed the separation line. And then when you can see here is the flow is separated, and then it reattaches on the ramp face. And you can see at the reattachment, flow is going in both directions on either side of this line here. And then it just goes straight back down on the ramp face. And this is sort of an interesting, because in a lot of the work that people do in simulations, they talk about some of these interactions as being these weak interactions. And I say that because the separated flow is about 2 delta in extent, that these are actually incipiently separated, meaning they don't exhibit mean reverse flow. But this is just showing that no, indeed, they do show mean reverse flow and a clear and distinct reattachment line. Okay, so this is just some going back in history. And so this is from Ehrengill and Dalling in 1991, and it kind of exemplifies some of the problems or issues with these interactions. And so if you have a compression ramp and a separation shock, and then you put a bunch of transducers at the wall, then, and these are fast response transducers, say Coolite transducers, then the first one here is in the upstream boundary layer. And they measured what the pre-multiplied spectrum looks like. And you can see that it kind of peaks here, let's say roughly, 40 to 50 kilohertz, right? And that's expected because that's the boundary layer frequency, basically U infinity over delta naught. And then as you move it to 2, which is underneath the shock foot, or what's called in the intermittent region, that you can see it's a hugely different spectrum. And in fact, it's now peaking down here at about 500 hertz. And so that's very low frequencies. And you can still see the sort of some remnants of the boundary layer here, but the dominant fluctuations are in this very low frequency band. If we go to 3, that's also in the intermittent region, it's still there. And then as you go down under the separated flow, that you're back up to high frequencies. And so, and that's basically is due to the shear layer that's over the separated flows radiating down. So that was understood well or way back. And I just brought this up because this is actually something that we did. So this was a long time ago, like 2002 or something. And it's actually not very good compared to today's standards. We can, this is a 10 kilohertz movie using planar laser scattering of a Mach 2 interaction. We can do this at 500 kilohertz now, for example. But it is nice in demonstrating sort of what we're talking about here in terms of these range of frequency scales. So for example, this is the flow at 10 kilohertz. The flow basically moves from here to here in the interframe time. And so this turbulent boundary layer, it kind of looks like it might be resolved. It's not time resolved really at all. And but when so you just see all this motion, but then when this is the separation shock here, and then you do see it is actually time resolved, right? And just showing because it is moving at much lower frequencies than the upstream boundary layer. And so this is a good demonstration of this issue that the dominant boundary layer frequency is this, say, of order 50 kilohertz for this flow. And then the dominant separated flow frequency is down there around 1 kilohertz. And so it's actually well time resolved with these 10 kilohertz diagnostics. And I just wanted to show you this one other kind of problem with these interactions. And this is some work that we've done where we looked at the vibratory response that's forced by the unsteadiness of an SBLI. And so we have a compliant panel here. This is like a very thin piece of brass, a fraction of a millimeter. And then we have a compression ramp at the downstream end of it. And then we paint it with pressure sensitive paint. On the other side of the panel, we put a bunch of dots and we do what's called DIC, digital image correlation method, which lets us get the displacement of the structure, the out of plane displacement. And so this pressure, this is the surface pressure from the PSP, and these things here are Coolite transducers ports, but this thing is, in a sense, you can think of as the forcing function, right? In this case, the flow is left to right, and this is the separated flow down here, and this is forcing that panel to vibrate. And then when we look at the response of the panel, so this is the panel deformation, you can see it just goes, just has to have this wild, a response. Now, it turns out there's some very clear vibrational modes that we can identify in this, but you can kind of see that these are large excursions of that panel displacement, and it will lead to fatigue, and especially as things get hotter and they get weaker. Okay, so what is the source of this separated flow unsteadiness? so most investigators have emphasized kind of one of two mechanisms. One is either forcing by the upstream turbulent boundary layer, or some type of global instability that's essentially intrinsic to the separated flow. It's basically a self-sustaining instability. And so Poggi he just kind of in a paper like kind of put it this way. He said, I think it's just kind of nice to think about it this way, that the interaction can sort of appear as an oscillator, or it can appear as an amplifier, or meaning it may appear as an oscillator, or it may appear as an amplifier. That sort of remains to be seen by research, although we do have a pretty good idea by now. But and so that if it's an oscillator, then you can think of it as it's a combination of a filter and amplifier, but with feedback. So once you sort of kick it to get it going, that those oscillations will be self-sustaining. You don't need to have additional forcing, for example, from the upstream boundary layer or anywhere else. In the amplifier model, it's really just filtering and then amplifying the input, whatever this is input into it. If the input's upstream turbulence, and then it's going to output something related to that, a filtered version of that. But you need the turbulence. So if you take the turbulence away, it's going to stop, right? And so we have a pretty good idea now of which one of these is right. And so I would say that in terms of the oscillator model, where you have a downstream instability, that the wealth of evidence suggests that is a dominant mechanism of, especially for large, largely separated, strongly separated interactions. And so groups at Marseille, Pino Martin at Maryland, Adams's group, Sandham's at Southampton, Pirasoli, and this is in many others. There have been like dozens of papers, in the last few years, even on this topic, and they do indicate that the interaction has an instability, and that it doesn't seem to depend on upstream fluctuations. Okay, now, and so having said that, there's actually is evidence that the amplifier model is important, and the question is, well, where is it important? Is it important in all cases? And so the evidence does exist that the upstream boundary layer fluctuations do drive at least the separated flow unsteadiness. And so this is associated with our group and Poggi et al, and then the group at Delft. Although I'm not attributing this view to them, but they did have experiments that demonstrated what I'm saying. Although the view is that their interaction might have been extremely weak and essentially just incipiently separated. And then there's also studies that show that both upstream and downstream mechanisms are kind of present in a sense simultaneously. And I would say that probably most people probably think that now, and it's just which one dominates and is sort of the issue maybe, and although with more people coming down on that the oscillator model is dominant. Okay, so and I'm just going to this is sort of like our point of view in terms of our search for unsteadiness over the years. And so I'm going to go back to 2002, and this is an experiment that was done by Steve Barish, who's now at Sandia. And he basically has a compression ramp interaction, and he had Coolite transducers that were underneath the shock foot. And then he did PIV simultaneously with Coolite measurements. So he did PIV in the upstream boundary layer. And so then every time that the shock foot, let's just say, moved upstream by one transducer, he would put all those PIV images in one bin. And then if it moved upstream by across two transducers, he would put those PIV images in another bin. If it moved downstream one transducer, he'd put them in a different bin, and then move it downstream two transducers, he'd put them in another bin. And then he would average all those, and then he would get profiles, but also he would get the velocity fluctuation. Now, if there's no correlation between what happens upstream and the shock foot, then you should just get your U prime should average to 0, right? U prime bar is 0 in a turbulent flow, but not if there's a systematic correlation. And so in fact, was what he showed, that for example, downstream motion is associated with upstream velocity fluctuations that are positive, and downstream and then upstream motion is associated with fluctuations that are negative. And so these here are like, and you can see they keep growing. They're getting growing as they get closer to the wall. And then right here, they're about 20 meters per second, which is 2.5% of U infinity. And you got to ask, is that really strong enough to do anything, right? That to the flow? There might be a correlation, but is that really a cause of much unsteadiness? And I will point out that Porter and Poggi in 2018 did the numerical analog to this experiment, and they looked at a compression ramp interaction, and they did the same type of analysis and really showed a very similar result, and did show in a sense that these sort of fluctuations can lead to unsteadiness because they were forcing the flow, and looking at what's the effect of forcing with these type of magnitude fluctuations. Okay, so Barish then kind of proposed this, and this is kind of the simplest way you could think about forcing these interactions as an amplifier. And that is that you have an upstream velocity fluctuation, and then that leads to an instantaneously fuller velocity profile, which has more momentum in it, and then reduced separation length scale. So velocity fluctuation increases, separated flow or separation bubble sort of collapses, right? And so, and then if it gets smaller, it's negative. You're going to have less momentum, and your separated flow gets larger. Okay, that's very simple. Now, one thing is the upstream fluctuation must persist for long enough for that separated flow to respond, right? And that is a long time typically, and I'll point that out here. So this is from Priebe and Martin, and so they had this nice study in JFM, and they basically show in this instance where you have a compression ramp interaction, and you have a separated flow that's set up. There's a separation bubble right here, and then in the next instant, that there's no separation, there's no bubble. So the streamlines here are deflected upwards, and the streamlines here basically just go straight, right? And then until they hit the ramp. And so the fact that the streamlines are deflected upwards means that there had to be, from Newton's second law, a pressure force that acted in order to deflect it. So the pressure here in this corner will be higher than the pressure in this corner once that bubble is gone. And then they also gave us the velocity profiles upstream of this interaction at the time of these images were selected. Okay, so then you can actually get that there's a velocity fluctuation, you know, that's magnitude, and then also what the pressure changes. Okay, and so so we've done in our own sort of analysis just showing that if you take the momentum transfer rate fluctuation, you just want to say, is that actually big enough to do anything, to actually collapse this bubble, for example? And even if you have it, is it strong enough to do anything, right? And so we just said, well, assume that the upstream boundary layer fluctuation has a fluctuation in the momentum transfer rate, and then you're going to compare that. This is a division. Change in the pressure force due to the separated flow displacement, right? As I just mentioned, the pressure is higher here than here. And so you can just sort of write it in sort of this form. It's a function of the upstream dynamic pressure, and then the velocity fluctuation, and then you have the pressure, and you end up getting, you can put it in this form where you have this ratio of the pressure change and then the turbulence intensity. It's actually not turbulence intensity because this is an instantaneous fluctuation. Well, you can just show that with a 3% fluctuation, that this quantity is of order 1. It's just showing it is plausible that an upstream velocity fluctuation could collapse that bubble. Okay, I'm not saying it actually did that. In fact, it may not, but just the point is that these things are dynamically important enough, these kind of fluctuations, that to do something. Okay, now it takes about 45 outer scale time scales, or delta 0 over U infinity. This, like, you need structures that are 45 delta long, say, if you want an upstream boundary layer fluctuation to do this, in order to do this collapse, right? And it has to persist for a very long time. And so you just say, well, what in the boundary layer is actually persisting for 45 delta, right? And so this is where Barth came in, that he was a postdoc in our lab, and he had come out from the University of Minnesota, and he was looking at superstructures in low speed flows and in their low speed wind tunnels. And we were thinking, well, we kind of wonder, thinking about this kind of mechanism that might drive the unsteadiness, that these superstructures might be the reason, right? And so he started looking for them in our supersonic flow. And so he did 6 kilohertz PIV in a streamwise spanwise plane. So that's sort of a plan view as you're looking down on the wind tunnel floor. Laser sheet comes in parallel to the floor. And so this is a high Reynolds number boundary layer. So Reynolds number RE theta of 30,000. The Y over delta is at the laser sheet is at 0.2, which is in the log region. So we're not talking, and so we're not talking at any near wall effects. These are out in the log region. So he had got this movie, and let me just see, does this play? This one does not play. Okay, it's okay. This is a movie, and it's basically doesn't show much correlation. You do sort of see these streaky looking structures, and but it doesn't, in a sense, doesn't give you that much. And it's not surprising. 6 kilohertz is just not fast enough to resolve this flow. In fact, the flow moves across almost the entire image in the interframe time. So it doesn't really look like a movie in a sense that's time resolved. However, we can use this information in it. And we did it this way. We said, well, let's take an image out of the movie. And then if we assume that Taylor's hypothesis is correct, then and that the flow is essentially frozen as it propagates downstream, then the frame that came after this one was actually before it in space, right? And so we can displace it by and this is essentially just Taylor's hypothesis, which you do with a hot wire, say, and you displace it by the convection distance. And then you take the next later frame and you displace it upstream again, and you do it again and again and again and again. And what this is assuming Taylor's hypothesis is correct, you have it is a quasi-instantaneous snapshot of the upstream boundary layer structure, right? And this is, again, in the log region. And you do get this very long kind of meandering, low momentum regions. And this is what is the characteristic signature of superstructures that we're seeing in all sorts of different flows in low speed boundary layers. And so, I mean, if you look at the size of it, it's like 40 delta, right? And so and then you think of it as a wavelength, it's half of that, and maybe it's actually 80 delta. And so it did seem like maybe there is something to this in terms of having this low frequency type of motions that exist that could lead to this very long duration shock unsteadiness. Okay, and this just compares our measurement here to what they had done at Minnesota and with a hot wire rake, and just showing the kind of the similarities, and these things that are simulated, and so they are definitely barred of boundary layers, although whether or not they're important for understanding the separated flow unsteadiness is a separate issue. He did look at this, and so this is where we bring the interaction into the picture. And so there's a compression ramp right here, just at the downstream edge. And then, of course, the laser sheet again is parallel to the floor of the tunnel, and we are looking from the top. And then this is a surrogate for the separation line, because we're looking a couple of millimeters from the surface, from the wall. And so we don't have the location of, say, zero skin friction or zero shear stress. And so this is a surrogate for the separation line, which is just a contour of velocity. It's an arbitrarily low velocity. And so what you see is that there's going to be a superstructure that starts to appear here, and you can see that the separated flow surrogate is definitely responding to the presence of that to that fluctuation. And so you can see where the high speed when high speed regions develop, it moves downstream, and when low speed motions develop, it moves upstream. And so at least that's a plausible argument for what's happening. At least the separated flow can be affected by these superstructures. Now, if you look at this separation surrogate time history, compare it to sort of a region of average boundary layer in the upstream boundary layer. We just take a little window and average the velocity fluctuation there, and just to reduce some of the high frequency noise. And what you get in these, maybe not doesn't look like it, these are actually fairly similar waveforms. And when we do the correlation coefficient, they're about 0.62. So they're actually quite strongly correlated. And so that was back then, a number of years ago. And since that time, we've got a lot better at doing this kind of thing. We got a pulse burst laser, which is a very, very high frequency laser, which can go up to 500 kilohertz, for example. And you combine it with high speed cameras. And so this is a 50 kilohertz movie, PIV movie of the interaction, and that's shown about with this field of view here. And so you see things like this is the incoming boundary layer. The flows again going left to right. You see the upstream boundary layer. This is the separated flows down here. And then you see a shear layer that's developing over the separated flow. It's then reattaching on the ramp, and it's developing a new boundary layer down here. Okay, so, and then there's sort of, we defined again, like a separation surrogate with these chevron marked by the triangles here, and then a reattachment surrogate marked as a low velocity region as by that triangle also. And then this is a plan view, and this is looking down, again, laser sheet is parallel to the wall, then we're looking down on it. And this is just to show sort of like some of the large scale motion of the separated flow. And so if I'm going to step through a sequence here and just notice that they're going to follow this structure here, and as it sort of propagates down, it kind of grows, and then the separated flow is getting larger, and then it gets very large, and then the bubble is so it's sort of like it's just flapping, right? And there have been numerous studies that have sort of suggested that the shear layer flapping is an important kind of mechanism in this low frequency unsteadiness. We're finding it's more important for the high frequency unsteadiness, but and I'll have more to say on that in a bit. Okay, so one thing is that the 50 kilohertz data let us do is we can bandpass filter it. And so this is, I'm going to go down here to the lowest band, so 0 to 1 kilohertz. So this is down at a Struhl number of 0.04. And it's nominally below the frequency of those superstructures, but just shows that, and you have to look carefully here, but this boundary layer is thickening and thinning. And essentially, as the boundary layer is thin, then that separation bubble is small. And then it's thicker now, and then the bubble gets bigger. But you see that both the separation and reattachment are moving together. They are moving in concert, but they move in or anti-correlated. As one moves downstream, the other moves upstream. And then as you go to the mid-frequency band, 1 to 10 kilohertz, and this sort of overlaps the frequencies of the superstructures, you see something similar to that, although you definitely see much larger changes in the separated flow scale than you did for that very low frequency band. And but it does appear to be a little, in a sense, a little more chaotic. And then when you go to the high frequency band, you don't really see any seeming correlation with the upstream boundary layer at all, and it does. You see the shear layer is extremely active, and so it does appear that most of the motion that you're seeing of the bubble is related to flapping of the shear layer over the bubble. And this is just some way to look at some correlations that I'm going to define this little window here. We're going to average the velocity in here and basically make a velocity fluctuation. I'm going to call that delta U boundary layer. And then we're going to measure the location of the separated, instantaneous separated flow surrogate line from its mean value. And call that delta L sep. And then we're going to measure measure the distance between the instantaneous reattachment location and its mean value, location, and call it delta LRE. for reattachment. And then this is just playing a time series of those. And of course, you know, you're not going to get too much from that, but that just shows you what they look like. And this shows their correlations, though. So this is a correlation of the upstream boundary layer fluctuation and the delta LSEP, so, and the separation line, and it's around there about a 30% kind of correlation. This is actually pretty similar to a similar correlation that Priebe and Martin did in their study, where they were looking at mass flux fluctuations, the upstream boundary layer. They did not claim this was a dominant effect, that it was an effect, though. And then if we look at the correlation between the upstream boundary layer and the reattachment, so the upstream boundary layer and reattachment location, you see there's essentially no correlation there. And this is for the unfiltered data. And then this is a correlation between the separation line and a reattachment line. You can see there's a fairly weak correlation. Well, I'm going to go more into this with some PSP, but before I get there, we're going to do some joint PDFs between a delta LSEP and delta U boundary layer. And so when delta LSEP is negative, that's a large bubble. If it's positive, it's a small bubble. If velocity delta U boundary layer is negative, it's velocity deficit. If it's positive, it's a velocity excess. If you get a thing that looks like this, like a diagonal kind of a PDF, that says there's a good correlation between these two quantities, and that it's consistent with that momentum kind of hypothesis that high upstream velocity causes a small separated flow. However, if it looks like this, then it's just they're kind of not correlated, right? So this is the low frequency band, and this is the mid frequency band. This is the high frequency band. And what you see is there's a very diagonal looking PDF, joint PDF, just showing there is a strong correlation between the upstream boundary layer fluctuations and the separated flow length scale. And it's also anti-correlated with the separation, with reattachment. And so that's just showing that this thing is also at the very low frequencies, it's just breathing, it's pulsating like a bubble breathing. And in fact, that it's strongly correlated to the upstream boundary layer. And then as you go to the mid frequency range, it's less diagonal, it's a little broader, which means the correlation's not as strong. And but you still see sort of a similar feature. And so this is sort of the band of the superstructures. And then as you go to the high frequency band, there's no correlation at all with the upstream boundary layer. Okay. Okay, so we also did pressure sensitive paint, and this is more recent work. And so you basically have a paint a surface with a paint with a luminophore in it, and then we excite it with a UV light, and then we image that. And you can, by calibration, you can relate the signal to the surface pressure. So we have measurements on the floor of the tunnel and on the ramp face. And this just shows you the frequency response as we compare it to Coolite transducers, and just showing it actually works pretty well up to about 10 kilohertz. And so, and then we're sampling, framing rate is 20 kilohertz, the Bobet-Nyquist. So this is just an example of what the movies look like of the PSP. And this is frankly just really nice in terms of quality data. And so this is the upstream boundary layer. This is the separated flows in this region. This is what you're seeing is the boundary layers developing back onto the ramp face. And so just sort of a wealth of information is here, compared to the few Coolite transducers that people used to be restricted to. And so if we can also define, like we used to do with Coolites, the separation line, the shock foot, the instantaneous separation shock foot line from the pressure threshold. And then we do a similar threshold and call that reattachment, right? And so you'll see that the separation line is very smooth, and then reattachment is very jagged. And in part, it seems to be due to the generation of Gertler vortices, and these are things that have been observed already, especially in DNS of these flows, and just it's due to the streamline curvature of the separated flow induces this centrifugal instability, these Gertler vortices that then interact in a way, and in Pino Martin's view will lead to the low frequency unsteadiness. And so, and definitely from these type of simulation or these measurements, that you can see the evidence of these streamwise structures of that looking like they're about the same a wavelength as you would expect for Gertler vortices. So when you do the cross correlation now based on between reattachment and shock foot, you get at the unfiltered data is about 0.55, and then the filtered, if we filter to 1 kilohertz, it's about 0.8. So there's a very strong correlation between the separated flow. Again, it's breathing, it's just sitting there oscillating, and we're not saying here anything about the upstream, just that these things that except the low frequency is dominated by this breathing mode. And then this is the coherence, just showing you know, how whether or not these are behaving as a linear system, and you can kind of see that as for the low frequencies down here, that the coherence is quite high, and suggesting it is these things are the shock foot and reattachment are behaving like a linear system. Okay, this is some low pass filtered movies. So this is 0 to 1 kilohertz. So this is just tells us what the flow looks like when we in that very low frequency band. Again, this is sort of below the band of the superstructures, and there's actually still activity in the upstream boundary layer that we do not understand. In other words, that the boundary layer seems to be sort of has these high and low pressure regions that are actually across the whole tunnel, and it does seem to be related to, you know, like the motion of things, but it's just the correlations actually don't come out that strong, but it is definitely present. But you can see now that the shock foot and the reattachment area are anti-correlated, and then as you see that as the shock foot moves downstream, you get a higher pressure region on the ramp face, as you'd expect. It's sort of a stronger interaction at that point, and when it moves upstream, it gets weaker. And then we go to a higher frequency low pass, and so this is 0 to 5 kilohertz, and now you start to get where these presence of these streamwise structures, there's the formation likely of these Gertler vortices, and they do seem to participate a lot in the reattachment unsteadiness. And then when we go to this is a band pass from 1 to 5 kilohertz, and you see that this is sort of what I was mentioned, like this is like this stuff is happening in the upstream boundary layer now. You kind of see this is between 1 and 5 kilohertz, but just these kind of waves coming through, then we don't quite understand what that is. But you do see in this case that the presence of these streamwise structures, again, looking like the Gertler vortices, and then at still higher frequency bands, it's just more random kind of turbulence. So so we think that the Gertler mechanism as proposed by Priebe and Martin could be definitely could be a mechanism here. Okay, and then just one more, which if we take just take 2 locations and pressure, one near separation and one near reattachment, and we do the correlation, and this is for high pass filtered, that we see that there's essentially no correlation then, a very, very weak correlation between those two. So it's just showing that the lack of coherence between those between separation and reattachment dynamics. Okay, so I'm ready to conclude. So we've been studying then the separated flow unsteadiness in weakly separated compression ramp interactions, and I say weakly separated because they are about 2 delta in extent, and as you get to 4 delta, then that would be we would consider that a stronger interaction. And so we do think that the upstream influence is much stronger with these weaker interactions, and that's something that has been proposed by ourselves and also other groups also. And so the superstructures are clearly a dominant feature of the upstream boundary layer, and they seem to play a role in driving the low frequency motions. And then the unsteady motions will depend on the frequency bands. For example, at very low frequency, you have a bubble breathing motion is very strongly coupled to the upstream boundary layer. In the mid band, that's the superstructure band, the bubble breathing motion is moderately coupled to the upstream boundary layer fluctuations. And then the high frequency band seems to be dominated, the large scale motions tend to be associated with shear layer flapping. And I will say that we do expect the importance of upstream fluctuations on the separation line to diminish as the interaction gets stronger, right? And that's because the velocity fluctuations don't change, but the pressure required that you want the momentum changes to overcome become larger. And at some point, it's just not going to be able to push that flow around. However, even if the separated flow acts as an oscillator, the question is, you have all this energetic stuff happening in your upstream boundary layer, and this may be a tunnel effect, right? That just happens to be the way our tunnel works. But you have all this energetic emotions in the upstream boundary layer, and if you have an oscillator, what is the effect of that on those oscillation amplitudes, right? And that's something that's not well understood at this point. So with that, I will conclude and take questions.
Thank you very much, Noel, for that really interesting talk. As the questions start to come in, I just want to clarify one thing. I forgot to say that the seminar is also co-hosted by the Department of Applied Mathematics and Theoretical Physics at University of Cambridge. So it's together between DAMT and LIFD, as well as the Journal of Fluid Mechanics and the UK Fluids Network. So it's just, I had it all written down and I forgot to say it in the beginning. So just to clarify that. So there is a question on the vibratory response slide, and somebody was asking if you could share that again, Noel.
Thank you very much for a great presentation. Would you please, on this slide, a little bit more explain about characterization of vibrational mode, because this is very interesting.
Okay. Well, in terms of the vibrational mode, it's actually this is a very thin panel, right? The wind tunnel panel is a couple inches, or sorry, a couple centimeters thick of steel. And then there's this panel here is just like a fraction of a millimeter, like a third of a millimeter. And then there's a cavity that's underneath it that is pressurized. So we can sort of match the pressure above and below the cavity when the tunnel runs subatmospheric, because the tunnel runs subatmospheric. Anyway, so that thing moves, and then we basically use DIC, and we just put basically paint the bottom surface with a bunch of dots, and then we image it with 2 cameras, and we get the out of plane displacement of the panel, and that's what I showed. That's what I showed here. Mm-hmm. And then you can, if you actually look at this is the total deformation, but if we take the deformation from the fluctuation, subtract out the mean, and then it actually looks more like normal vibrational modes that you'd see, where they look more that the first mode is actually symmetric and it's just moving up and down. And then you see the second mode is like anti-symmetric. And so you can go through the structural dynamics analysis, just showing that it behaves in a sense like you would expect in terms of having like sort of random forcing of the flow. And so we're looking at how the modes change, for example, in the presence of the shock boundary layer interaction, and then just trying to understand the coupling between the panel motion and the flow itself. Because obviously the pressure field is affecting the panel, but the presence of the panel motion affects the flow, and then that again affects the panel, right? And so it's a coupled problem in general, except for unless you have very small displacements.
On the last question, is it possible some resonance effect there?
Yeah, this is a resonance, right? Of the panel motion is resonating in a sense, right, at its vibrational modes. And so answer is yes. And that's what we actually picked it because you know that from those pressure, you know, the shock foot pressure data, you see where the peak frequency is, right? Where the most energy is. And we literally picked the thickness of the panel to coincide with that. And so we're creating a situation, a shock foot motion is driving this thing very energetically. And so it's driving the first mode.
All right.
Sure.
There's another question, Noel, from David Gupta. Has there been any research on artificially disrupting upstream superstructures that might reduce bubble oscillations?
That's a good question. And Dussauge's group did a little bit of that, but I don't think it was in the way you would really want to do it because they just put some vortex generators up in the nozzle and tried to sort of create new ones. But I think that we have done some stuff with sort of plasma actuators where we've shot pulse plasma jets upstream, and we did show definitely responses of the interaction in essentially trying to create disturbances. And so, but it's difficult to relate those to the superstructures themselves. And then, as far as your real question was, can you disrupt them? And no one has been able to, or at least been able to do that, or tried to do that I know of.
There's another question from Belu Shiva Prasad, which says, it appears as though there is an organized span-wise vertical movement of the bubble, and then that splits the bubble. I don't know if you've noticed that.
Yeah, it is in the pressure
Okay.
pressure picture. If you notice very carefully, there is a vertical motion both in the low frequency filtered picture and the high frequency also. Okay,
let me look at the low frequency here. So you're saying in this one?
It looks as though the anti.
I see what you're saying, like a wave propagating sideways. Yeah. That's interesting. That is very interesting.
And perhaps these bubbles that they may be splitting. If you look at the high frequency motion, it may be splitting in the span-wise direction also.
Anyway, so yeah, I think that we need to look more for this kind of thing. I think that those are really good comments. Thank you.
There's another comment from Lucaria, which said these could actually be the Gotler vortices.
Yes.
At least on the on the ramp.
Yes, I think they are. And we never saw those in velocity, right? Because we're just not. If you just one cut, you don't really see them. But the PSP does seem to show them.